going to do section 10.2, and we're out. Okay, questions from you guys? John, is that a hand?
Yeah, I was thinking about it.
Okay.
Could you go through 6?
6? Yeah, man. So we're basically just filling in the table.
Yeah.
So like I'm just taking my value for t and plugging it in. So like cosine of 0 is 1, sine of 0 is 0, and just going on.
Okay.
That's all we're doing.
Yeah, I dig.
You dig?
I dig.
And you could do that with your calculator if you wanted, make sure in your radian mode, or you could just use the unit circle, or have it memorized like if you're a math teacher or something.
Yeah.
Cool? NBD, right? What else? Okay, well, it's not a big deal if you don't have more right now. We can always hit more stuff up later as you get a little bit further along. That's okay. So it doesn't have to be all today or nothing. Any last calls? All right, fair enough. Well, let's just pick up where we left off in section 10.1. So we were doing Cartesian to parametric. So in our first example, we looked at, let me go back and pull that answer. There it is. So 3x minus 2 was the example we looked at last time. And we had said that as long as that Cartesian function like passes a vertical line test, the parameterization is really easy. We can just make xt and make y the same as the y before, just with t's instead of x's. And whatever the domain for my Cartesian then becomes the interval for my parameter. And I'm done. Right? Easy peasy on that. You guys remember doing that? Okay. We'll do 2 more examples where maybe it's not quite as straightforward as like you're given a function. Okay. So what if we want the parameterization for a line that goes through the points 3, 9, and negative 5, 2? Well, we could do the obvious thing, right? We could calculate the slope using those 2 points, write the y equals mx plus b equation for the line, and do what we did before in the previous example. Could do that. Is there an easier, sneakier way to do that? Mr. Kulik thinks so. So if you remember our vector equation for a line, r is equal to r naught plus vt. R naught was a point vector, so it doesn't matter which point we use. And v was our direction vector. So to find that, all we have to do is the head minus tail rule. It doesn't matter which one you make the head and which one you make the tail. And so writing the vector equation for the line then, pretty easy. And this tells me exactly my parametric function. So remember, this vector equation in line says to get the x squared, and I do 3 plus 8t. And to get the y coordinate, I did 9 plus 7t. And since this is a line, the domain for that line would be all real numbers. So we can do all real numbers for t, and we're good to go. Now I argue that's a little bit simpler than, computationally simpler than creating the y equals mx plus b equation. Now use some high level concepts, but the actual arithmetic and stuff we did there was pretty easy stuff. You just subtracted basically a couple of numbers and put it into a form. You know what I mean? Now, the difference between that and writing the mx plus b equation, not a whole lot, right? Not a big difference there. A little bit of savings maybe, but not a ton. The place where, or the type of problem where it does present a nice savings is if we're talking about, instead of a line, but a line segment. Okay. So again, you could find the slope-intercept equation for the line, use that to create your parameterization. The problem is, though, fixing the interval for the parameter becomes kind of complicated because you have to make sure the endpoints actually make the domain and range work for your function, which can be kind of a hassle. If we use the vector equation for the line, though, getting the interval for our parameter is going to be super easy. So this is where it really kind of pays off a lot. So again, the R naught is a point vector, so I can use either point, doesn't matter. The direction vector is head minus tail. It doesn't matter which one I make the head and which one I make the tail. So there's my vector equation for the line. I translate this into my parameterization, where I parameterize that then. Oops. Everybody so far so good? Same thing as before. Now here's the point or the place where having the vector equation for the line is going to be nice. If t is 0, we output the endpoint, one of the endpoints automatically, right? And then to get the direction vector, we subtracted the 2 points. So if t is 1 or -1, then it's just going to be the same thing as like adding that back on to get the other point. So what this boils down to is this interval here will always be either 0, 1 or -1, 0. Presuming you use the vector equation for the line, that'll always be the interval for your parameter, which is wicked nice because now it's just like a check problem, right? So say I usually just check with 1 because it's like one less negative sign. Since that's not an endpoint, I know it's not that one. And I'm done. Didn't involve having to solve anything like we would if we had used the mx plus b equation. John?
That thing, the 0, 1, or -1, 0, is that consistent for all line segments?
As long as you're using the vector equation for a line, yes.
And how did you know it was -1, 0?
Because when I did 1,
Oh, you checked 1.
I didn't get an endpoint for my graph. I didn't get
Okay.
the other endpoint. God bless you. So at most, all I need to do is check either 1 or -1. It doesn't matter which one you do, because if it works, it's that one. If it doesn't work, it's the other interval. So you don't actually even have to check all the endpoints. You just need to check either 1 or -1. I'll tell you, and immediately you can tell which interval you need, which is pretty nice, right? That's an easy check to do. It's almost, bless you, a mental math check, right?
Yeah.
Which is pretty nice. Versus if you did the mx plus b equation, now you're like, have to make sure the x coordinate is equal to this and that and all these other, it just becomes, bless you. It becomes kind of a hassle. All right. That finishes up 10.1 for us. Any questions on any of this stuff before we move on to 10.2? Okay. So in section 10.2, we're going to look at an application of parametric functions. The most obvious application. Hi.
Hi, thank you.
You're welcome. Ryan is with physics, specifically talking about kinematics, which is the study of motion. So if you're thinking about how an object moves, its position is typically represented as like an XY, like a point. But the independent variable that describes like how it's moving is going to be with time, right? At certain times, the thing is in a different place. So like time is our parameter in our parametric function, and we have a way to describe x coordinate, y coordinate based on that time. Does that make sense? So in this course, we're going to talk about two different types of motion. We're going to talk about one-dimensional motion and two-dimensional motion. Nobody really in high school is going to talk about three-dimensional motion because it can get pretty scary. So we're just going to start with one-dimensional motion. Those of you in physics, that's like just things being dropped or whatever, right? Or shot straight up or down. Everybody's cool? Okay. We have two equations that we'll worry about when it comes to one-dimensional motion. So we have a position function and we have a velocity function. God bless you. So again, for these letters, S is a position. In the case of one-dimensional, usually that means it's a height. G is the gravitational constant. V is velocity. Velocity is just basically speed, but it can be negative. In physics, speed always has to be positive because it has no direction associated with it. Whatever. And then T is our parameter that'll represent time. Now, when we put the little subscript 0 on a variable, it just is going to mean initial, right? So V naught is the initial velocity, or S naught is the initial height. Everybody's okay with that? So in this course, we're going to just talk about all of our units as feet. In that case, the gravitational constant is -30, or is about -32 feet per second. So really, this first equation becomes -16t squared plus V naught t plus S naught. And this second equation becomes -32t plus S naught. Everybody okay there? So all we did is just define an equation. Let's look at an example of using, or where we can use this. Okie majokies. So we have a ship stranded in the ocean. On top of the bridge that is 80 feet above the water, a distress flare is shot straight up with an initial velocity of 72 feet per second. Provide a graph of the flare's height against time and find the height of the flare above the water after 1, 2, 4, and 5 seconds. So, which equation do I need to use, the position or velocity equation here? Read the question again. It's position, right? Because it's asking like the flare's height and finding the height of the flare. That's a position. So we're going to need to be using that position function. So notice this is a Cartesian function that we've described here. What's the initial velocity? 72 feet per second. And the initial height? 80 feet. So I could just take this function, put my calculator back into function mode. Notice I'm changing to degree mode here today. We'll see later why. And if I type that into the y equals menu, I'll just set my window here. Since x is representing time, I don't know how long this stupid thing's going to be in the air, maybe 8 seconds or something. I'm just guessing. And how high would it go? Well, it's going to, again, zero height is a decent minimum. We're shooting straight up in the air. We're starting at 80 feet. I don't know. Let's try 200. Just see what we get. Hit graph. There's a graph of height versus time. So that answers the first part of the question. If it wants the height after 1, 2, 4, and 5 seconds, I can plug those into t individually. Or if I press second and graph, it'll open up the table for this graph. And I can read T1 is 136 feet, T2 is 160, T4 is 112, and T5 is 40, and not have to do so much typing into my calculator. Everybody okay with that? If I look at this picture, though, is this picture really descriptive of what I would actually be seeing with my eyes? Nah, man, because the flare doesn't go left and right. It just goes straight up and down, right? Can we describe that same motion of straight up and down with a Cartesian form on our calculator? Nah, man. But what can we use to describe it? Parametric. Yeah, so I'm going to switch my calculator now back to parametric mode. Okay, and clear out the stuff that I have in here right now. So I'm going to just parameterize this guy the same way that we did before. So I'm going to just make the x component, or the x equation, equal to t. And then just replace the x's with t's and type that equation into the y. And then I'll reset my window so my t goes from 0 to 8. That sounds good because it's just the same thing as my x going from 0 to 8. And I think all my window settings from the previous mode followed me through, so that should be good. Hit graph, same pictures I had before, right? Everybody's cool? But that, again, not describing what the flare is actually doing. So let's fix this so it actually describes the flare's motion, right? So when we shoot the flare, is it moving in the x direction at all? So it does not. So I'm going to just fix the x direction with a constant. I'm just going to use 1. You could use 2 or 3 or 4 or whatever. It doesn't really matter. Okay. If I hit graph now, you see it sketches in this vertical line. Well, okay. That's what the flare does, but not a very informative graph for me. But if I move my cursor over, you see this slash next to the first function. If I press enter a few times, I'll get a little circle there. And what this is the trace option. So this is just going to show the points that the calculator uses to create that previous graph. If I hit graph now, that circle actually traces the path of the flare on my calculator screen. That's pretty neat now. What do you think? Yeah, not too bad, right? Pretty neat. Okay. Now, two-dimensional motion, not a lot we can do with this. So that's our example for one-dimensional motion. Two-dimensional motion, much more versatile. Oops. So let's define how we do that. For these 2D motion equations here, we have to use parametrics. What do you notice that I've used here already when writing this first parametric function? How about a vector, right? The vertical bars around the vector v is the magnitude of vector v. And you might be going, woof, Mr. Kulik, vectors again? Nah, man, it ain't so bad. So let's actually make those v naughts, right? These are all initial velocities. And I'll just write this as v in general. But remember the component form definition for a vector is this, right? So all this has changed from the previous definition to now is instead of having an initial velocity, we have like the x component of the initial velocity and the y component of the initial velocity, right? That's really all that's going on here. So it's not like you're going to have to deal with any vectors when we actually look at these story problems. But all the letters and everything still mean the same thing, right? The magnitude of the initial velocity is still just like a number, like it would have been in the previous problem. Everybody's okay? Let's do a series of examples here now to get used to these 2D problems. All right, you hit a baseball 3 feet above the ground with an initial speed of 135 feet per second at an angle of 16 degrees above the horizontal. Will the ball clear a 15-foot fence that is 300 feet away? If yes, by how many feet? If no, how high up the wall will the ball hit? First question, position or velocity? Position. We're asking where the ball is going to hit, right? Taylor. Sure. So the equation for position in 2 dimensions is the magnitude of the initial velocity, which is 135, and then cosine of theta. Theta is 16 degrees. And then I have my t. And I have, for the y, negative 16t squared plus initial velocity sine theta, which is 16, plus the initial height, which is 3. Okay? So what are we really wanting to do here? To answer this question, basically we need to figure out the height of the ball at the wall, right? To get the height of the ball at the wall, we need to figure out the time in which the ball's at the wall. So I'm going to call that T300, Y300. That's how far away the wall is, right? So to figure out how long it's going to take the ball to go 300 feet, well, I guess, and then once we have that time, we can just plug it into the Y and compare that to the height of the wall, right? Everybody's okay there? So we need to figure out how long it takes the ball to go 300 feet. That 300 feet is in the horizontal direction, right? Because really what we have here is like the ball's here, 3 feet high, 300 feet away, and then there's the wall that's 15 feet tall. So we want to see like, whoop, what's going on with the ball. Everybody's okay with the picture we kind of drew there? Okay. So really what I just need to do is solve 300 equal to 135 cosine 16 times t. And once I have that answer, I'm just going to plug that in for y. And that'll give me the height that the ball is when it gets to the wall. And we're done. Okay. Before I start plugging all that stuff in, though, I'm going to go and do a little bit of stuff on my calculator, just kind of set things up, because I like to have a picture to just confirm what's going on here. So I have 135 cosine 16t as my x equation, and then negative 16t squared plus 135 sine 16t plus 3. I guess turn this off. Okay. We'll reset our window. Baseball players. There's a 16-degree angle of exit for a ball is pretty line drivey, right? Line drive goes about 300 feet. How long is that ball in the air for, give or take? Reasonable estimate? 3 seconds? Probably a reasonable estimate. I'm going to double it just to make sure. So I'm going to go 0 to 6 for t. My x is the horizontal distance, so obviously it's starting at 0. The wall's 300 feet away, but I want a little bit more than that, so I'll go to 350. The y is the height of the ball. There's a line drive. Obviously, we're starting at 0. Probably doesn't get too high up there. I'm not sure. I'm going to do 50, maybe just for starters. Let's take a look at our picture here. So that's the path of the ball, basically. That's pretty neat. So we're interested in, I guess, if these tick marks I think made was 50, 52, 250. So 300 feet is like right in there. So we're interested in the height of the ball right there at 300. To get that time it took to get there, we're just going to do 300 divided by 135 cosine 16 like I wrote down below. Oops. Notice when I'm doing this, I'm using the fraction command so I don't have to muck around with a bunch of parentheses. So it took about 2.3 seconds to get to the wall. That was a pretty good estimate. John, you said 3 seconds it was going to be in the air or whatever. Luke said 3 seconds. Pretty good estimate. A little bit of common sense, right? Helps if you played baseball at all. John?
How do we arrive at 335?
Well, this is the, this is, right? That's our x, right? So we just need to, how long does it take the ball to go 300 feet in the x direction is going to be the same time it takes the ball, you know, when it's going to be here at the wall. Right? Because that parameter is the same because it's parametric. So the value of t we plug in to get to 300 is going to be the same value of t we plug in for the y when the ball is at 300 feet away. Yeah. So that's all I'm doing. So there's 231. And rather than typing that all, like writing that all out again, like plugging that into this long equation, forgot the t there. What I'm going to do is I'm just going to have the calculator plug it into that equation for me. Since I've already typed it in on my calculator in the y equals menu. So to do that, I'm going to just press the vars button, go over to the y vars option. We're in parametric mode. So I'm going to select that, and then I put mine into y2t is the equation that I'm interested in. So I'm going to just do that of my previous answer, and it spits out 3.5. So that's the height of the ball after 3.5, or about after 2.3 seconds, which is when it's getting to the wall. What does that mean? How tall was the wall? Less than 15 feet, so the ball would hit the wall 3.5 feet above the ground. Now, it would be nice if when I graph this, if I could get like the wall to show up here. So if I can make a vertical line segment that's like 15 units tall, that'd be pretty sweet. So I could actually visualize what's going on here. We can do that. So that wall is 300 feet away. So the x coordinate just is going to be straight 300. The wall is 15 units tall, but I need to graph a point at like 300, 0, 300, like 0.1, 300, 0.2, all the way up to 315 to get that vertical line to all the way show up. Is everybody okay with that? The way I'm going to do that is I'm going to take 15 and I'm going to divide it by the t max that I'm using to graph with. So to retrieve the variable t max, I'm going to press that vars button again. I'm going to pull from the windows. I'm going to go to the parametric and polar variables and pick t max. And then I'm going to multiply by t. So remember, t is my variable. T is going to take all the values from 0 to 6, I think. And t max is just 6. right? So as t iterates through all the possible values of t, it's going to start at 0. So it's going to be 15 times 0 over 15, which is 0. And then t will go to like 1. So it'd be like 15 times 6, or 1 over 6. And it'll make a point. 15 times 2 over 6. So it'll keep making that all the way up. The biggest value t can take is 6. So it'd be like 15 times 6 over 6. Which would just be up at 15. So it's just going to create a vertical line that's 15 feet tall. Yes?
Do you mind running back how you got T-max times T off the board?
Yeah, so the T is just the variable button right now.
Okay.
T-max is in the vars menu. We keep the T-max on the window, right? When we press window, that's where we find the T-max at. So we go to window. And then we want the variables for the parametric and polar stuff. So we just scoot over there, and there it is. All right, so go back here. All right, so I'm going to do that, and then I'm going to graph this one with the tracer on. So it's going to make the little circle, and then it's going to draw the line behind it as the circle goes, so we can see the path of the ball in real time, and also it'll trace the path so we can look at it afterwards. So if I hit graph, there's my wall. Here's my baseball. How neat is that stuff, guys? And again, we can see clearly the baseball is not clearing that wall. Pretty rad. Let's do another example of a real similar situation. Here we got old Jeffy is going to be hitting a baseball 3.5 feet above the ground, initial speed of 141 at an angle of 24 degrees. You want to know if that ball is going to clear a fence, a 20-foot fence, 400 feet away. Well, we'll set this up the same way we did. So we have initial velocity, cosine theta times t. Then we have negative 16t squared plus initial velocity sine theta t plus initial height. So let's start by updating our model in our calculator. Oops. So that we can get a picture of what's going on right away, and then we'll solve it algebraically afterwards. So I'm just kind of updating what was in my calculator before to reflect the current situation. So my wall is now 400 feet away and 20 feet tall. My initial velocity is now 141 rather than 135. My angle is 24 instead of 16. And my height is 3.5 instead of 3. So I just updated everything on my calculator. I'm still going to have it do the same way, where the wall is going to draw in solid, and then the baseball is going to be that tracer function or tracer option, so it traces it along. Let's see what Jeff can do. Oh, what did we forget to do? Yeah. So I'm going to bump this up to like 0 to 8 on my interval. Since the ball is going further, it's hit at a, like a higher angle. I think it's going to be in the air for longer, so I'll bump that up to 8. The wall is now 400 feet away, so I need to make the X max bigger than 450. And we're hitting the ball up into the air more, so I'm going to bump that Y max to maybe 100. There's my wall. There's my baseball. Whoa! Jeff, what a stud. So it looks like we're hitting dingers here, right? All right. So that's cool. Let's see if algebraically that matches what we're seeing there in our picture. So I'm going to start by finding the time it takes to get to the wall. I know the wall's horizontal position. So I'm going to take the x equation and solve that for t. So the time it takes to get 400 feet away or move 400 feet in the horizontal direction is here. So I get 311. And then I want the height of the ball at 3.11 seconds. And again, I could plug that into the equation for y by hand up above, but I don't want to do that. I'm lazy. I'm going to have the calculator do it for me. So I'm going to go and press the vars button, go over to y-vars, pick the function command, and then I put it in y2t. So I'll do y2t of that 311, and I get 27.3 feet. So we can say the ball clears the fence by 7.3 feet. Everybody okay there? Okay. How many of you guys, anybody's a baseball fan here, watch baseball on TV? What do they almost always report after somebody hits a home run? They report how far that home run went, right? How do you think they're doing that? Well, they don't got some kid out in the stands with a tape measure. They're calculating it based on, their stat track or whatever. It gives the angle that the ball leaves the bat and the exit velocity of the ball, and they compute it like what we're about to do right now. So taking that same situation with Jeff the Legend there, assuming there's no obstructions in the way, how far will the ball travel before it hits the ground? So what are we doing this time? Yeah, we need the time when the height is 0. We'll call that T0. And then we're going to plug that into the x equation to give us the total distance that ball, or total horizontal distance that ball covered, right? So when you're watching your baseball game and Mike Trout hits a 510-foot home run, they're not out there measuring it with a tape measure. They're doing a calculation like this. So John had it right on that the ball hitting the ground means the height is 0. So we're going to plug in 0 for y of t. So what kind of an equation do we have here? Quadratic. How do we solve a quadratic equation that looks like this? Got to use that quadratic formula. Okay, so T0 is going to equal negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So I'll go to our calculator. Here, I definitely want to use that fraction command because Ooh, boys, that'd be a lot of parentheses to keep track of. So I have negative 141 sine 24. Now with the plus or minus, I just have to do one at a time. I'm going to do once as a plus, and then I'll do it again with a minus. So 141 sine 24. Notice I'm taking that whole thing and putting it into a parenthesis and then squaring it. Minus 4 times negative 16 times 3 divided by 2 times negative 16. Oh, it's 3.5, guys, right? My goodness. I was like, that's not the same number I got last class. Okay. Oh boy. Ew, Lizzie, what did you just do here? Okay. I wish I could look at this all at the same time, you stupid calculator. 24, okay. Sine 24, y squared, okay, minus, okay, 4 times A times C. Oh, I see. I don't think that 0.5 was underneath my radical. Well, that would have been a tough one to spot. There we go. So I get negative 0.06. Uh-oh, does that make a lot of sense? Well, it kind of does. Like, think about what's going on here. So we're starting here at 3. If I draw the parabola that's happening, yeah, I guess I'm not surprised that I have one of my answers over there that's negative time. Clearly not the answer I care about, but doesn't mean that I did anything wrong there. Want to make sure I point that out. So what I'm going to do is I'm just going to go ahead and press second and enter to recover the whole thing. Rather than typing it again, I'll go back and edit that plus sign to a minus. And 3.64 is my other result. That's the one I want. So I'm going to do x of 3.64. And again, I could plug that into the x equation, but I don't want to do that. Personally, I'm just going to use my calculator to do it. So I go through the vars menu and pick x2t and plug that in, get 469.4. Jeff's a beast. Cleared the wall and kept on going another 69.4 feet. What a beast. Okay. Oh boy. Go away. Let's do one more here. So again, using this same example with Jeff the legend there. The man, the myth, the legend. So assuming, again, there are no other obstructions in the way, what's the furthest distance away from the starting position that you could place that 20-foot fence and still have the baseball clear the fence? So basically we're saying, how far back could I bump that fence? So maybe like right here-ish, right? Still looks like maybe the ball would clear the fence there. We were looking for that horizontal distance. So maybe we can bump the fence back 10 feet or 20 feet or 30 feet or whatever. Is that okay? So what we're going to need is the time when the ball is at a height of 20 feet, right? I'm going to refer to that as t sub 20. Once I have that, I can plug it into x to find the horizontal distance in which the ball is going to be at 20 feet. And if I put my fence there, the ball should just squeak over the top of it. Everybody cool? So how do I find the time when the ball is at a height of 20 feet? Which equation am I going to be using, x or y? Y, because it's talking about heights. And what value of height am I interested in? 20. So 20 should equal negative 16t squared plus 141 sine 24t plus 3.5. Okay. What do I got to do to solve this? Yeah. Got to subtract the 20 first, and then we can quadratic formula that guy again, right? Here's the nice part about this, though. Compared to the last problem, all we did was we changed 3.5 to negative 16.5. So that's an easy edit. I'm just going to recover the formula that I had last and then just update that one little part. So 367 or 327. Or the other one would have been if I was adding. Which was at 0.32-ish. Again, that hopefully makes some sense. There's 3, there's 20. It's going to cross that 20 line twice, right? Which one do I want? Yeah, the later one. So again, I could plug that into the formula, but I don't want to do that. Again, I'm just going to retrieve this x of t and then plug in that 327. So I get 421. Now, which way should I be rounding this? Should I be rounding it up or down? Has to be down. So if I'm going to one decimal place, I would want to make that 421.0. Or if I did 2 decimal places out, 421.06. Why can't I round that up even though the trailing digit is greater than 5? It actually is putting the fence further away when the height would be less than 20 there because you're going the wrong way. And the ball is going to just kind of tick, hit the very top corner of it and maybe not bounce over. And that would be tragic for Jeff. How do you guys feel about this? Again, none of the algebra we did there was terribly difficult. The tricky part is deciding whether you should be using like your x or y equation, how to use parts of one equation to find things to plug into the other one. But all these problems kind of follow the same pattern. right? We're using either the x or y equation to find a time to plug into the other one, just depending on whether we're asking about, where the ball, how far the ball is away horizontally or how high the ball is vertically, will dictate whether we should start with either the x equation or the y equation. Does that feel okay? At this point, we should now be able to do 41 through 48. So you could tack that on to your to-do lists. For Sunday, your problem set is just 1 through 40. So on the 13th or whatever. The 20th, 41 through 48 will be on there, plus whatever else we add on next week. I would say next week, we meet 4 days. We've covered the first 2 sections. What do you think there's a pretty good shot of happening next week? Homework quiz. So I would want to make sure that I'm, pretty well caught up by next class with the sections 10.1 and 10.2. Again, you don't have to have it all perfect, but you should have at least done some of the, done enough to where it's like, yeah, okay, I get the idea. Yeah. Anybody questions for me? Okay. Well, we're going to stop here. Reminder, the virtual days, Thursday and Friday, the only assignment you have for me is to work on your stuff. I'm not going to ask you to do anything on your own. Just work on your problem set. I think 40 problems for Sunday is probably woof-tastic enough. So that sounds good to me. You guys good with that? We're all cool? Everybody's cool? Bunch of little Fonzies?